So today's topic would be more specific to the healthcare scenarios, and the topic would be activity understanding in this kind of healthcare scenario. And I'm Sneha Sismaji. I'll be presenting briefly about this topic, what are the major tasks in this kind of scenarios, and we'll see in the presentation. So when we start with the activity understanding, it has something to deal with the videos, right? So what do we mean by a video? So if I have to define it formally, I guess everybody knows what is a video as we are joining through a video conference. So
have you shared the screen?
Yes, it's not visible.
Not visible. Let me ask participants. Maybe there's a problem from my side. Yeah, participants, can you able to see the screen? Yeah, visible, sir. Okay, then that's a problem from my end. No problem. Go ahead.
Me, I'm also confused, sir, because at the beginning I was not audible. So
no problem. No problem.
It's okay.
Please go
Okay.
ahead. I will read.
All right. Okay. Okay. So where we were. Okay. So to define formally a video, the definition of video is it is a 3D signal, and as everybody might have understood what is a image that deals with the spatial coordinate, it has X and Y. So if we repeat the images across the temporal coordinates, the axis t, then it becomes a video. So one can change this frame rate to make the video fast or slow. Okay, so that's the frame per second of a video, the attribute. But if we fix the t, let's say if I say the t equal to 1 or something like that, then we get a single frame. So for example, if somebody is throwing something, so each frame has to the motion from taking the hand from the back to throw to the front. So this is a typical instance of a video. So I don't have to spend a lot of time here. So when it comes to the healthcare applications, where do we expect these videos kind of scenarios to occur? So the first one is the elderly behavior monitoring. For example, if you have a elderly at home or in the street on the or in the wild scenarios, we want to monitor their behavior to prevent them falling, this, that. So this is one of the crucial aspect. The second thing is the surgical scenarios. If someone is looking for a robotic surgery, then one has to monitor the activity of the robot while during the surgery, so or the different phases of the surgery, right? So these are the two major applications where I see this kind of the activity understanding problem has this two major applications in the healthcare perspective. Although I'm not a very expert in the healthcare perspective, but I deal with this kind of video and activity understanding problem statements. It's been a while. So the three major tasks when we want to do this kind of activity understanding is the first one is the action classification. This has the similar kind of notion as the image classification, but here the input is a video. So the idea is to identify the actions that is being performed in a given set of frames or in a clipped video. So the video need not be long, like it can be like 2 to 3 seconds or 5 seconds. So those are the clipped or trimmed videos, and the idea is to identify what kind of actions are being happening inside the video. So this is action classification. The second thing is the action detection. So in all the real world scenarios, all the videos need not be clipped or small videos. It could have varying length videos. It could be 2 seconds, 3 seconds, or maybe it can go up to 9 hours of videos, or more than that. So in untrimmed videos, the action detections task is more promising, because here it locates and identifies specific actions. So basically, it recognizes the actions and identify where temporally this actions is being happening. For example, like from 9 second to 15 second, the action this is happening. So the idea is to temporarily detect or identify different actions happening in a long video context. And the third one is the more it's slightly complex, different from the action classification and detection, that is the action anticipation. Here, the idea over here is we allow the system to observe some past occurrences of some events, and the idea is to ask the model what will happen in the future. It's a kind of predicting the future action. For example, if somebody is kind of holding a bag, wearing the shoe, maybe the next action could be leaving the home, kind of thing. So this is kind of action anticipation. Uh, all these three tasks are quite relevant in the healthcare perspective. Action classification to understand what is happening. Action classification and detection is mostly to understand what is happening right now or maybe in the current time frame. Anticipation is to say that if in the future something wrong can happen, it gives you a preventive measure, right? So classification, detection, these are mostly for timely taking some action. Anticipation is more on the preventive side of the application, right? So to understand the action classification, as I say, if we have a certain number of frames that is stacked across time, you give a model video classifier. Right now, let's say just one black box video classifier, and we want to see what are the classes, and the highest score we have given to a class is taken as the, let's say this is the action happening inside the class. So but this is the on the similar notion of the image classification. But one of the major thing that we need to understand over here is what is the difference between the image and video classification. What makes it different? So if we see that if I have to draw a clear boundary between these two tasks, so on the left, if we have the image data, so typical machine learning pipeline is the feature extraction, classification. So on the feature extraction, you could extract some feature descriptor models, like all the deep models like VGG, ResNet 50. These are the pre-trained image models. And then nowadays in the last lecture, as we cover the foundation model. So the feature extraction can be done from any of these models. And once you have the features from the image, you give it to a classifier. Let's say it could be MLP, it could be SVM, it could be anything to draw the class separability plane. But when it comes to the video, instead of having just one input, we have several inputs. And this several inputs is it is not homogeneous in the data set. Maybe one video is of 1 second, another video could have 3 seconds. So the number of frames in video 1 and in video 3 are different. So how to deal this kind of scenarios over here? So basically, you extract again the through the feature extraction frame by frame. One could stack the frame feature across by concatenation or some pooling mechanism. And the idea over here is to obtain a single feature vector from the entire video, irrespective of their duration, irrespective of the frame count and other attributes. Just having one feature vector for the entire video so that you maintain the homogeneity in the data sample. And once you have the one representation, then giving it to a classifier model like MLP or SVM to draw the hyperplane. So the idea over the difference lies between image and video classification in the representation space. How to obtain this kind of unified one representation for the entire video, right? Without losing information, and that is the key thing, I guess. So if we look at the evolution of research on this video classification technique, I think the first one, it started with the frame level aggregation with the 2D convolution network. So whenever I say this 2D convolution network or the frame level aggregation, all these things can be bind with the recent foundation models what we talked in the last lecture. You have the feature extraction and then you do the aggregation like kind of thing. So on the frame level aggregation, the idea is aggregating the frame level information and then applying some sort of pooling. But what happens over here is as you do a pooling between all the frames to get a vector, so the most crucial information in a video, that is the temporal information. When you do the pooling, this information is lost, and it might cost the performance on a scale. To deal with this kind of things, uh, okay, but all these methods are pretty old, but this is necessary to build the foundation of the next couple of slides. Then there is this two-stream architecture. So maybe one stream is for the spatial and another stream for the temporal modalities. So as you might know, that optical flow modality is one of the most representative of the motion information in a video, like the pixel, the change in the pixel across time. But obtaining these different modalities, the optical flow, could be challenging, or it might affect the complexity in the network. So it is slightly complex than the frame level aggregation. Then on the third, that people have already also tried a different kind of applying the frame level feature with recurrent neural networks or temporal convolution networks. This is one after another, like first applying spatial modeling through the CNN or the transformer, and then applying the temporal modeling with the RNN or TCN or maybe any other temporal transformer networks. But here, when it is one after another, like spatial after temporal, so they do not handle the space and time simultaneously. So this is kind of dissociating the things. So then the 3D convolution network have it has arisen that can do both space and space-time modeling simultaneously, but they are also restricted to some kind of limited kernel size. So they cannot process 1,000 frames, rather they can process 16 to 64 frames at a time, or maybe 8 to 64 frames at a time. So these are the most of the previous method before the transformer, I would say. They used to deal the video classification method problem like this. So to begin with the frame level aggregation, when we say that if you have a video, the set of frames, you have an image classifier like or a foundation model here like Clip, Dino or anything, you can extract the per frame feature. So if you have T frames in the video, you will have T frames, T feature vectors. And then one can apply either a max pooling that can give you the more salient information. Okay, but wherever there is a big change across the frame, the max pooling will give you the higher pixel intensities values or the salient region in the image. The mean pooling is more to focus on the subtle changes. The average pooling is to get a global context of the video. It's a kind of smoothing the entire frames. There is also this kind of min max pooling that you can do with this kind of concatenating the max of the features and the mean of the feature to get a more representative feature vector for the entire video. And once the feature vectors are extracted, it is represented, it can be given to a classifier like MLP to do this, the classification. But how to extract this frame level features? Okay, these are basic things, but I'm doing this. Okay, the frame level feature extraction for any kind of VGG or the pre-trained networks, one can extract the features from the last layer, or one can extract the features from the beginning layer. Mostly in major of the cases, the features are extracted from the towards the end. And this is mostly because in the towards the last layer of any backbone, maybe it is a pre-trained CNN or foundation model, the features has the more abstract representations. So only relevant informations are kept towards the end of the network. And in the beginning, this the features are mostly, it contains all the information present in the image, so which could be redundant for the classification. So towards the end, it has more compressed, and only relevant features are maybe encoded from the entire image. So there are different frame level aggregate, different types of frame level aggregations are there. So if we say that there are several frames in the video, and this is a backbone network, so one can choose from the entire video just the middle frame, not considering all the frames, because in the actions in the middle of the video might be the most expressive frame to represent the action. So, and based on this middle frame, one can extract the features and classify. So this is the single frame approach. So one can also do this kind of beginning and end frame. So you have two, let's say, feature extraction model. One takes the beginning, one takes the end. At the end, towards after extracting the features, you concatenate and you classify. So this is typical late fusion. Then there is this early fusion. In the the late fusion is more expressive for the high motion activity. If there is activity that has more motion, so by differentiating the beginning and end frames, you can classify the activities. But the early fusion is most widely adopted. So instead of taking just one or two frames, it operates in a window. So the window is placed in the middle of the video, and it takes several frames, extract the features one by one, concatenate, and then classify. So choosing this window length is also a hyperparameter of the network. So how big window you want in the model to be captured the activity. So in the slow fusion, there could be several windows, and then you overlappingly extract the features, concatenate in the later stage, and do the classification. So all of these types of frame level aggregations, they are targeted for different kind of applications. If you have a simple activities, maybe single frame might work. So we may not say that which of the type is the best for all kinds of applications. So it really depends upon the applications, which kind of fusion can work. So what we observe on the basic methodology is that the frame level pooling, it might provide you some video descriptor, but it only mostly encourages salient frames in the video, not all the frames, right? And the video descriptors for each videos are treated as simple data points and for a classifier, and there is nothing much. But this video descriptor, they do not model the temporal information, so which only relies on the salient frame level features. So how to do this kind of temporal information, model this kind of temporal information? So as I say in the beginning, the two-stream 2D CNN. So there is one stream dedicated for the spatial modeling, and then from the input video, one has extracted the optical flow modalities, and then there is this temporal stream dedicated to learn the cues of this optical flow frames. And once you have extracted so at the end there is this classifier layer, which is softmax activated. So it is a kind of late fusion. So you extracted all the semantics from the video, the spatial semantics, and the optical flow semantics, and then you do a score level fusion. So, but here the motion information is not long term. It's mostly like a short term. So the motion information is between some few frames. So it's not giving a global motion information, right? So it can only capture some short-term temporal dynamics, not the long-term temporal dynamics. One of the drawback of this method, other than the complexity. So obtaining the optical flow is also, it incur some amount of complexity into the network. Okay, until this, do I have any question? Because then I have to, if I check the chat box. Okay, no question. All right. So on the third type, what if we recall correctly, is that this is the two-step modeling approach. The first one is the two-step means in the step one, spatial modeling, step two, temporal modeling. So on the temporal modeling, one of the classical approach is the recurrent neural network. So this is a on a family of neural network that has a loop inside the network. So if you have a input, let's say this is a frame information at time t, you have the neural network A, and it gives you a output for this timestamp. And also the output of this neural network is given to the next successor network. So basically, it copies the network multiple times across the time. If you have t frames, it creates 10 copies of the neural network, and then it sequentially connects the first network to the second to the third. So it's in a loop, kind of. So yeah, and by connecting this kind of network, it do some sort of sequential modeling in the in the data sample, right? Okay. And this is a classical, if we see that the image on the left, the network, like taking input xt, giving a hidden state output t, ht. If there is a loop, then the sequential connection, it looks like this. So if we look at this, to compute the ht, the forward operation, it with a weight matrix, it relies on the input of xt and the previous hidden state, right? So okay. And how these the input from the previous hidden states are combined in the next copy of the network? It is just by some concatenation. So this is the xt, and the previous hidden state outputs are coming here. So there is a concat, and then it is 10h applied and computed the next hidden state. Okay. So one of the major limitations over here is, as it copies multiple instances of the network, create multiple copies of the network. So if you have a smaller video, let's say if you have small 16 frame videos or 32 frames video, it might okay for those kind of videos. But if you have a longer video, for example, 5 minutes, 10 minutes, it might forget the relationship between the first frame to a frame that occurs maybe after 1,000 frames or 100 frames. So the long-term context modeling in this kind of network is missing. And if you have a longer video, then you have multiple copies of the network. So there can be a high chance to happen this kind of vanishing gradient problem. So like the error propagated in the last hidden state might not reach to the first hidden state of the network. So there we can have this kind of vanishing gradient problem. So how to handle this? Okay, this is a basic sequence modeling approach. The improvement over RNN is seen in the LSTMs, that is the long short-term memory. And what are the two major characteristics of LSTM that overcome or that builds on top of this RNN methodology? Is the first one is the information persistence. So by using some sort of cell states, the LSTM can persist the information from the first frame to the last frame, and it is like a conveyor belt. So it allows the information to flow through across all the frames. So if we see that in the RNN, if in the second hidden state, it only relies on the previous one. And due to there is another bunch of 10H activation here, the information of the first hidden state might lose after the second one. So, but with LSTM, due to the cell state, this information can propagate until the last copy of the network. And then this is the prioritizing the network. So out of the 1,000 frames of the video, let's say, not all frames might contribute to the activity. So how to find out which information is most relevant for the task, let's say. So it decides the which information is useful for the future, and it can discard the information that is not useful. Okay, and this is happens through the multiple gating mechanism in digital logic, but this is mostly controlled by neural network, right? So a typical LSTM cell, it looks like, okay, it also do multiple copies like RNN because it builds upon the concept of the RNN. But a typical LSTM cell, it looks like this. So in a LSTM cell, instead of, if you see in the RNN, it takes just the hidden state of the previous input and computes the output of the current state, right? But here in the LSTM, it takes two inputs. One is the previous state, hidden state, and the cell state of the previous state. Okay, and then it applies multiple operations to compute the current hidden state, the output of the current hidden state, and it also propagates the cell state and the current hidden state to the next copy of the network. Okay, so here it has four basic measure module. On the cell state, if you see that, it allows it just a multiplication and addition operation. There is no activation function. So basically, it just allows the information from the previous cell states to propagate to the next one. In the forget state, the idea over here is to discard the useless information, and how they decide the which one to discard. So basically, they take the output of the previous hidden state, the input of the current state, they are concatenated and sigmoid activated. So as we know, in the sigmoid activation, it gives you the value between 0 to 1. So all the inputs that is the values that those are close to 0 are kind of discarded, and all the for all those inputs, the values are above close to 1. Those are kind of preserved for the preserved, right? So the on the input gate also this kind of it also applies this kind of sigmoid activation to select the information that has to be that has to participate in this state for computing the hidden state. And this also apply a 10H activation same as the RNN, and that is multiplied to compute the cell state and the hidden state. In the output state, it basically also applies similar kind of sigmoid activation to prioritize information. Okay, which information to pass to the future and restrict all others. So that is also controlled through this kind of sigmoid activation. Okay, there are also more detailed things inside, but we don't have time to go there right now. Okay. If I have to say that there are different types of LSTM. So there is one-to-one. So you give one frame to the LSTM cell and you just get one output. So basically you apply some sort of frame selection algorithm here, like just the middle frame or the 1 or 2 frames, and then you give it to the LSTM cell to get just one output. And this is mostly used in the image classification task, right? To memorize the feature distribution in the LSTM cell kind of thing. And there is one-to-many. So you just give one input to the model, and the LSTM cell creates multiple copies of itself and gives the output for each of the state. And this is mostly this kind of LSTMs are mostly used in image captioning. So for each image you generate multiple captions or multiple text. Then there is this many-to-one. So many-to-one means it takes multiple frames as input and gives you one output from the last hidden state of the LSTM. And this is widely used in the video classification. So you can feed all this kind of frame information, and then just one class label is obtained from the last hidden state. Then there is this many-to-many. So it takes all these information of the frames and gives you the class label for each of the frame that can happen in the action detection things, right? So how to use this kind of LSTM in the action classification? The many to one. So for each of the frames, there is this CNN. You can extract the features from the CNN, one feature vector, and then one can pass it to the LSTM. That those are connected one after another, and from the last frame after the feature extraction, the LSTM takes the input and previous state input to give you the class label, action label. So this is the typical way of combining the LSTM CNN with the LSTM for doing action classification. But the one of the major drawback of this RNN type or LSTM type sequence modeling is this cannot be parallelized, because the current timestamp, it depends upon the previous one. So until the previous timestamp is not computed, the current timestamp, the execution of current timestamp cannot happen. So there is a dependency between the network. So this is kind of sequential approach. And as these are only relying on just the previous timestamp or just few previous timestamp, it can only capture the strong temporal change. If there is a drastic change in the video, it can only capture this kind of changes. But if there is a subtle change, the actions are really subtle, then this kind of things cannot be handled by LSTM. And despite having this kind of cell state that allows the information flow in LSTM, still they cannot, there is a vanishing gradient issue for the longer temporal context. Okay. And if because all this pre-training, the CNN has the one of the biggest characteristics is the able to pre-train, or the foundation model has the able to pre-train. But if we want to pre-train LSTM and use on a small data set, it may not be efficient, because pre-training is not that a good idea, because the distribution learn in the gates, it might change. So for the small data set, so it cannot happen that the efficiency will be affected. So to still able to do this kind of temporal modeling without relying on the LSTM, or by overcoming the drawback of RNN and LSTM, is the temporal convolution network. So instead of applying the convolution on the spatial region that the typical CNN they do, applying the convolution on the across the temporal axis might solve the problem. So the TCN, this can encode the temporal dependency by applying this 1D convolution filter. And all of you know this input and output shape. Okay, I don't have to go there. So TCN can be causal. So causal means it only rely on the past frames, not on the future. So the future information, the leakage from the future cannot may not happen here. And with the TCN, because the CNN has the ability to scale the network to some extent, not that much as the transformer, let's say, but still it is slightly scalable. So TCN can go very deep, and it can help with the residual connection to go far from the past information to predict the class level. So if we see that if it is, these are the each of the let's say this is an input tensor, so you have a TCN kernel, let's say 1/3, then with the input and the kernels are being multiplied to the compute the output tensor. So, and it can happen, these operations can be, this layer can be stacked with multiple layers to increase the receptive field. So if there is this receptive field is here, it is 3. If we stack multiple layers, so we gradually increase the receptive field to cover the entire video. So this is one way. And thereby the TCN mostly they follow the encoder decoder structure. If we see that, so these are the inputs for each of the frames. After the convolution and pooling operation, let's say this is the receptive field 3. So when we do in an encoder structure, multiple convolutions layers are stacked to compute a single latent vector, and this latent vectors is computed by covering the entire receptive field of the video. Right. So in this way, it allows more relation modeling between the neighboring and distant feature app. So maybe here the relation modeling is between the 3 frames. Maybe in the level 2, the relation modeling is between the next couple of frames, which is more than the 3 frames. So kind of it is increasing the receptive field. Okay. So the similarly, the TCN can also be replaced by the way we apply the, let's say one can apply the LSTM. So you extract the features from the CNN, then apply TCN, multiple layers of TCN, and TCN can give you the feature vector for each timestamp. There you can apply some sort of max pooling or average pooling with the classifier layer to do the action classification, right? So if I have to draw a clear distinction between the TCN and LSTM is TCN is, as it is inspired by all this convolutional operation, it can give you parallelism. So it has a parallelism feature, but LSTM they don't have, because these are sequential model. The output of current state, it depends upon the output of the previous state. And here the TCN can give you flexible receptive field. As you stack more number of layers, the receptive field can grow, but with LSTM, the receptive fields are always constant. It only rely on the previous timestamp. In TCN, there is no vanishing gradient problem. The gradient is more stable than the LSTM, because LSTMs, it creates multiple copies of the network. In TCN, in terms of memory requirement, it is low, but in LSTM, it needs to maintain some hidden state or the cell states. It has a high amount of memory requirement. And CNNs are more, or the convolution layers are more known for transferring adapting the new domain of the data sets. So TCN can also transfer the knowledge between the domain, but in LSTM, no, it is slightly not possible because of the distribution changes in the different gates of the SGM, right, between the data set. So then we reach to the third or the fourth part, that is, okay, we started with the frame level aggregation. If I have to recap quickly, we started with the frame level aggregation with just feature extraction from the frames and then classifying. And then we have this two-stream approach that process the spatial and temporal parallelly and combine the decision at the end. And then we saw the one from the CNN followed by LSTM or TCN. And one of the to overcome the drawback of all the previous approach, the 3D convolutional neural networks are mostly designed. Maybe these are also designed 6-7 years ago. But the concept of these 3D convolutions are still being used in the transformer that we'll see in the upcoming slides. So basically the 3D CNN, they use the 3-dimensional convolution filter. So they extend the notion of this 2D convolution to the 3-dimensional to capture the spatio-temporal features in a short snippet of videos. So if you know the equation of this 2D convolution, the same equation can be extended to the time axis. And so basically it computes the convolution operation in a tube, right? So, okay. So the 3D convolution is basically the kind of, if I have to see okay, what is this? Okay, so basically the 3D convolution, they can, if one has to design a 3D convolution network right from the scratch, so one can temporarily extend the version image network design, like the VGG, ResNet, and Inception, the mobile net, to design a 3D convolution network based on this kind of architectures, right? To start with, if one has to replace the 3D convolution, the 2D convolutions of the VGG16 with the 3D, then it becomes the C3D architecture. So C3D is basically, it contains all the 3x3x3 convolution kernels followed by 2x2x2 pooling. And it has 8 convolutional and 5 pooling layers and 2 FC layers. And it only considers 16 frame snippets to extract the spatiotemporal representation. And C3D is basically the temporally extended version of the VGG16. So if we see that the VG16 has also the 8 convolutional, 5 poolings and 2 FC layers, so the C3D has also. But the only thing is the C3D is pre-trained on kinetics dataset, kinetics 400, but VGG is pre-trained on ImageNet dataset. So the C3D is pre-trained from the scratch on the kinetics, and it can no, I'm sorry. The C3D is pre-trained on sports 1 million dataset. Sorry, small rectification. The C3D is pre-trained on sports 1 million dataset to learn more global spatiotemporal features. So on the sports, if we know that the actions has more motion information, so the C3D is more capable of capturing this kind of sharp motion in the sports activity like swimming or in the javelin throw, this and that. But one of the major thing what we have seen is that as it is extended from the VGG16 and there exists a pre-trained model of VGG16 that is pre-trained on ImageNet, those information is not utilized in C3D architecture. And that was one of the major point for I3D, where I3D is it is a 3D CNN version of the Google Net, the Inception, which is also pre-trained on ImageNet. It not just only replace the 2D kernels of the Google Net with the 3D kernels, it also do a inflation strategy from the spatial domain of the pre-trained model to be utilized in the I3D network. So basically, they replaced the 2D kernels of Google Net by the 3D kernels, and they initialized the 3D kernels with the 2D kernels by inflating them across time, right? So unlike the C3D, it allows multiple branching of the networks, and there are two major components of I3D, that is the bottleneck and the inception block, and it can process 16 or 64 frames for spatiotemporal feature extraction. So if we have to understand this bottleneck block. So if we have a feature map of dimension 28 by 192, and to retain the same spatial dimension, let's say 28 by 28, and we want to squeeze the depth of the channel from 192 to 16. By applying this 1 cross 1 cross 1 16 filters to the original feature map, that becomes 28 by 16. So the number of parameters used here is around 2.4 million. Okay. But if we compute the same 28 by 28 to 16, and we want to upscale it to 32, and we apply a 5 cross 5 filter with a padding size, of course, then the parameter computation is 10. So the one way is to reduce the parameter of the network with the is to use the bottleneck layer. If we want to retain the same spatial dimension by reducing the channel axis. Okay, so this is used in the bottleneck layer is used in the I3D, and a typical inception network is that takes the input from the previous layer, that applies multiple bottleneck layers along with the 3D convolution, concatenates the output from each of these blocks, and then it passes it to the next layer. So if we see that the I3D network on the video, it first apply a 7 cross 7 convolution filter, followed by a bunch of the 3 cross 3 filter with max poolings, tried this, and in between there is this inception blocks. These inception blocks are the one on the right. Okay, so by applying multiple inception block, it reduced the number of parameters while allowing more information to be passed in the multiple layers of the network. Okay, despite being okay, the I3D is also pre-trained on kinetics 400 dataset. So the kinetics is more large scale than the sports 1 million dataset, and by pre-training on kinetics, it gives more generalized feature representations for the video understanding, multiple video understanding problem statements. And I3D is still being used until today because of the parameter efficiency, better feature representation ability, despite being the evolution of the transformer, right? So, but one of the still the limitations of the 3D CNN is it has the rigid spatiotemporal kernels. Like it has a fixed spatiotemporal kernel. Like it can process up to 64 frames or 16 frames, and thus it limits the to capture them the subtle motion. The subtle motion means all the actions that has slow motion, so that happens in multiple frames, more than these 64 frames. So by having this kind of rigid kernels, it doesn't allow them to capture this kind of motion. And then there is no specific operations to discriminate, to learn this kind of discriminative features. I mean, here all the informations are passed through the convolution operation. There is no mechanism to learn discriminative features that can separate two different video based on their um, uh, different features, spatiotemporal features, let's say. So to learn this kind of discriminative features, I think the self-attention it has gained more popularity, and thereby the Wheat transformer. I think we have studied this. We have talked about this self-attention and Wheat transformer in our previous lecture. I won't go in detail, but the key three things are the multi-head self-attention, the MLP layer, and the layer norm that has extended to the video understanding problem, video understanding architecture like Vivid, the video vision transformer, right? And in the video vision transformer, as we all know, the VIT takes token of different, so it applies a tokenization on the image to take different tokens in a sequential manner, right? But in the video, the tokens are generated in terms of tubelet. Instead of applying tokenization to one frame, it apply based on a tubelet. So it takes a certain amount of consecutive frames, then it apply the tokenization based on some cube, right? And applying this tokenization, then it tries to flatten them with some linear layer to do the low level feature encoding, and apply the layer norm with the KQV with the multi-head attention, then the same thing as the vision transformer. But there are also few variants of the Vivid that has the factorized encoder or factorized self-attention. So on the factorized encoder, what it does, first it applies the transformer on the spatial domain, and then it applies the transformer on the temporal domain. So basically splitting them into the spatial temporal, the one we have already seen in the way they process with the CNN and LSTM. Let's say here the factorizing, splitting them into spatial and temporal. And this can also happen inside each self-attention block. It need not to be different self-attention. So inside each self-attention, the splitting can happen, the spatial and temporal, and it can repeat multiple layers. And then this factorized dot product. So first so by parallelly applying the spatial self-attention, temporal self-attention, and then fusing them inside one block, and then multiple blocks can be stacked to create the transformer encoder. But here the one of the major thing is the tokenization has a fixed window or the fixed tubelet size. And this is also true in the vision transformer. To overcome this kind of things, I think, okay, we have understood this part. Okay, the swing transformer has arisen. Okay, do I have any questions until this point? No. Okay. So in the swing transformer, mostly that uh, it aims to build a hierarchical feature maps by merging different image patches. So if we look at in deeper layers of width that produce feature map for single low resolution single low resolution feature map, here in the swing transformer it builds a hierarchical feature map, and it is enabled mostly by the shifted window concept. So what it does, it takes an image that do the patch level partitioning, and then let's say here the image is divided into h by 4 and w by 4. So in each stage it tries to divide the image with different factors. So when we image the image is divided into different multiple factors, towards the end there is a feature pyramid, and it applies this kind of swing transformer block that has a window self attention and the shifted window self attention. So if we look at that on the width, there is the fixed patch size 16 by 16 across all layers of the transformer. But in the swing, maybe in the first layer there is 16. On the second layer, it is 8 by 8. On the towards the last layer, there is this 4 by 4. And then combining all the three creates a hierarchy of the feature, right? And this patching mechanism is done by this kind of shifted window self-attention mechanism, right? And the 3D is the video model of the swing transformer is the video swing. Okay, so it applies the similar concept on the video domain that splits the height, the spatial resolution and the temporal resolution, the spatial resolution into multiple in the multiple stages to create the feature pyramid, and the only window self attentions are replaced by the 3D window self attention and 3D shifted window self attention. So until now, I think what we have understood is mostly what are the different models that is used for video classification. If we have to use this kind of models and concept in all the three tasks, let's say video action classification, action detection and action anticipation, these models can be used only these concepts can be used across different stages. So let's understand the see this action detection problem statements and how this is different from this action classification. So if we see in action classification, we have a video that gives a video classifier to get only the logits or the score for one particular class. In action detection, the idea is to say where the action is starting, where the action is being ending, and then what is this kind of action. So basically localizing the action across the timestamp is action detection, right? And if we have to see what are the major steps that is involved in this action detection task, so the first one is the feature extraction by using the pre-trained models that we have all discussed in the see that the ResNet, the i3D, all the video swing, vivid transformer to extract more meaningful spatiotemporal features that can include the RGB features, or maybe it can include multiple modalities like optical flow, pose, depth, and then to get a feature vector for the for each of the frame and then stacking them across time. The next step is to, because the action detection, it mostly happens in the longer video sequence. The video is of 20 minutes, 30 minutes, it can last up to few hours. So how to allocate this or how to load this entire video to a GPU is also a critical problem statement. So then mostly the model, it operates in the sliding window based approach. So basically dividing the video into overlapping or non-overlapping windows. So let's say you start from the index 1 to, you have a window of, let's say, 90 frames. So it takes the first window of 90 frames or 90 snippets, and then sliding the window with a stride. So on the first window, then it goes to the model, then the model is being optimized. The second window, it slides with a stride, and then it also goes to the model. So here, each of the window, it is treated as a candidate, or it is a data point for detecting the actions. And these windows, it can vary from 8, 16, 64, anything it can. It depends upon the, it's a hyperparameter. So after this window is they are then to compute the temporal proposals or the temporal anchors. So if we have the video, we extracted the features, we have the video features. Maybe out of the entire video, how to find out the temporal regions that might constitute some action might occur. Okay, let's say we have three temporal proposals, then the next step is to refine that action might occur. Okay, let's say we have three temporal proposals, then the next step is to refine the boundary of the temporal proposals. Let's say we have three temporal proposals with the boundaries. How to refine them? So we have the anchor. So then the boundary refinement mechanism is it takes place. Basically, it matches the ground truth start and ending point, matches the proposal boundary with the ground truth start and ending point to adjust them. And then there is a classifier model to classify which action is being happening. So basically, you have a two head network, one two for the boundary refinement, that is a regression network, and the classification network is to classify the action. Right. So these are the three major steps in the action detection. And one of the important step of this action detection is how to model this kind of multi-scale temporal modeling, because there can be actions that can happen at different duration, like short duration activity, long duration activity. So how to recognize or detect these all these kind of activities more appropriately. So one has to do this kind of multi-scale temporal modeling, either through transformer or temporal convolution or temporal feature pyramid networks. Then to more learn the discriminative features, one has to focus on the temporal attention by applying self-attention or transformer encoder to focus on the important frames, not to considering all the frames, only the pertinent frames that has the high information content to improve the accuracy. Okay, so then there are several literature that exist in the action detection. Maybe we do not have time to go there. If we have to understand the action anticipation, which is far slightly different than the action classification and detection. If we look here, the action anticipation in the action classification and detection. Okay, if I have to go a few slides. So in all these tasks, the video frames has already occurred, or it has already arisen in the timestamp, and this is being fed to the network to get a decision like whether it is a to class label or finding the boundary of the actions. But in action anticipation, mostly we want to predict the action that has not been erased until yet. So we have a observation time. So basically, it allows the network to observe certain actions, and then based on the observation or based on the ordering of the actions, it can predict the next action. Okay, so it's kind of predicting the future action. Okay, and this is it's a quite challenging task. And why? Because of the partial observation, the ambiguity in the actions. Okay, there is no observation length is ideal for all kinds of application. There is a huge ambiguity. We don't know which action might happen. That is the uncertainty. There is temporal variability. The actions might vary different length, and there is an uncertainty between the observation and the future. Right. So one of the typical applications in the healthcare is anticipating a fall of in an elderly care, if somebody will fall in the near future, kind of thing. Okay. This is a slide to clearly distinguish between the action anticipation between the detection and classification, right? So the steps of this action anticipation is mostly the first one is the feature extraction, the same as the detection. Here there is the second step is the key is there is a past encoder. So the past encoder only takes the observed past, not the future instances. It could be a clip representation, the foundation model, and then it goes to a past encoder like a transformer based. The step 3 is it's a optional because there exists a high amount of uncertainty between the current observation to the future. One can apply some sort of uncertainty encoder that try to modify the latent space of the observation to embed some uncertainty information associated with the future. And then there is this future decoder. So the future decoder, it takes let's say the uncertainty encoded feature and some anticipation queries to predict the future anomaly, right?
So
yeah, okay, we are out of time.
we are out of time, so you can just summarize.
Okay. So maybe we don't have time to go to this method, but okay, maybe we can summarize here. So okay, so what we have discussed is like we have understood this action detection, classification, detection, and anticipation. And maybe if you have interest in this kind of topic, I mean, dig deeper into, take these slides or presentation as a baseline to dig deeper into the problem statement. Yes, if you have some questions, I'm happy to take. So do we have time for questions or no?
Yeah, we can take 1-2 questions. If participants are having any queries, I think. Can you see any queries in the chat box? I think I'm unable to. They may, they may contact you directly. They will drop an email to you.
Okay.
I mean, how to just relate this action detection problem with the medical imaging domain, although you already mentioned in first few slides that how this kind of problem can be directly related to medical imaging classification or medical imaging domain. And the kind of CNN you have shown to us, like 3D CNN, basically, which is really useful in medical imaging also, not only in video kind of medical data, but also in data like CT scan and MRI, which is by default 3D in nature. Right. So I hope
there is a question.
Yeah.
Okay.
Yeah. Similar kind of questions, follow-up questions. 2D images can be taken for 3D models.
Is 2D images can be taken for 3D models? No, I think the data has to be in the three-dimensional.
Dimension mismatch, right?
Yeah, it is a typical dimension mismatch problem. But if you have as the 3D image segmentation kind of thing, those things can be, I guess, adapted for the video models.
So 3D models, whatever you have said, I think can be directly applied on the 3D data like by MRI, CT scan, if they want to only directly apply on that. I mean, instead of going for 2D models, PCNN models, they can directly adapt. So any other questions from the participant side? Yeah, there are a lot of data actually, which is in the form of video in medical imaging.
There is a small question for video classification. What kind of input is required if it frames or video itself? Is there any noise removal? Okay, so I think yes, this is a quite interesting question. So for video classification, both the kind of inputs are okay. But if the video, it depends upon the length of the video. If the video is small, the directly the uh, video can be taken into the loaded into the GPUs for doing the classification method. If the videos are short, so there is no noise requirement of removing the noise. But if there is a longer video, yes, there can be different proposal networks that can be proposed to find out the salient temporal regions and yeah. And which method? I think RC3D is the basic classical example to compute the region proposal in the video. I think it answered the question partly.
Yeah, any other questions? Yeah, I think there are no other questions from the participants. If they're having any questions, they can directly drop you email and they can reply.
Yes.
So thank you once again for sharing your expertise in the domain of medical, in the domain of video, right? Basically video classification and action detection, which is also relevant in medical imaging domain. So thank you once again for sharing your thoughts and your insights.
Thank you, sir. Thank you so much for giving this opportunity. It's a pleasure to talk to you and to the audience. Thank you.
Thank you. Yeah, so we'll move on to our next session. So next session will be delivered by Dr. Sandeep Singh from Cardiff Metropolitan University, UK. Hope, you could see there are some queries. Okay, please, you can just write these queries to directly to Snehasis. I mean, I will share the email ID if you want, right? If you just Google it, you will also get the email ID and all. Okay, that is fine. Yeah, Professor Sandeep, can you hear us?